now heard viewpoints about assessments from students, educators, educational researchers, and testing professionals. It's clear that this is an exciting time in the field of assessment, with many changes to be made and many different perspectives as to how those changes might come about. To go into more detail, we'll talk with two experts in the field. First, we sent Scott Osterweil to talk with Janice Gobert, who is an expert in the design of learning and assessment technologies for science. She and her team have developed an intelligent online tutoring system called INC-ITS that is used by thousands of students today. Then, I will talk with Dan Schwartz, a professor at Stanford University who's an expert in learning technologies. We will talk with him about the deep insights that can be gained from something called choice-based assessments.
So an assessment is in most general terms, a series of tasks or a task designed to get an evaluation on a person's skill level, a body of content knowledge, aptitude, predisposition, something of that type. It's designed to assess something in the individual, inherent in the individual. So we developed INC-ITS because we saw a really unique opportunity and need to have an assessment environment that was capable of assessing students' science inquiry skills. So it generates performance metrics for students' inquiry skills, like how they're hypothesizing, how they're conducting an experiment, how they're interpreting data, how they're analyzing that data, how they're warranting their claims, how they're communicating their findings. And we wanted to also be able to react in real time. So it can be used either as an assessment environment or it can be used as an adaptive intelligent tutoring system for science inquiry skills.
And what theoretical framework did you use in developing this?
So I'm a cognitive scientist by training, and so we used a really deep theory of how people learn, especially how people learn with rich visual representations. So the theoretical framework concerns model-based learning, how people build mental models progressively, say in science about static information and then dynamic information, causal information, and temporal information. So you can think of different sciences as fitting into these ontological schemes in different ways. So the one that I just talked about, the spatial, causal, dynamic, temporal, describes geoscience really nicely. In biological sciences, you also talk about structure and function, for example. So those types of ontologies then are important in developing students' knowledge, deep knowledge about a scientific domain. And so when we say that it was based on model-based learning theory, we're really hoping that the students and designing the technology so that students are acquiring these deep knowledge bases along these lines. So another literature base that was used in the design of INC-ITS and our micro-worlds in particular is the student literature on misconceptions. Mm-hmm. So we want students to engage deeply in inquiry around content. People learn about things. They don't learn about nothing. So for example, in the case of state change, often middle school students think that if you have more of a substance, the boiling point is no longer 100, it's higher. So we allow them to experiment with those relevant variables associated with those misconceptions. So that was another source of literature that was involved. Now in terms of how we break down the tasks and design the scaffolds for the various inquiry tasks, we come from a kind of a guided learning versus a discovery paradigm. Mm-hmm. So you want to give the student kind of enough control, but you want them headed towards a series of inquiry tasks that are going to allow us to generate metrics about how they're conducting inquiry along these lines that I stated before, forming hypotheses, conducting experiments, analyzing their data, warranting their claims, communicating findings. So if it's too open-ended, what can often happen, especially with low prior knowledge students, is they really get lost, yeah, and they have difficulty monitoring where they are. So we use guided inquiry as a theoretical framework as well.
To give a little bit of structure to what
That's right, to give a little bit of structure. Mm-hmm. But a student, say, if has a lot of prior knowledge, he or she could decide to specify a whole series of hypotheses and then analyze those, design and conduct experiments to address those hypotheses. Or alternatively, a student who has lower prior knowledge, they might just specify one hypothesis and sort of use it as a way to acquire content knowledge within the environment. So it works very nicely in that regard.
Great. You mentioned before the need to form models. Can you give an example of a model that a student might form in around a certain content area?
Sure. I'll give you the example that's plate tectonics, which is one of my favorite areas of science. So at first, what we want students to understand is the concentric circle model that has a nice affordance of being similar to the thing it represents. So if you were to cut the Earth in half, imagine cutting the Earth in half, and you have the core in the middle, and then you have the mantle layer with the magma, and then you have the outer crust, right?
Right.
And so you want students to understand that visual representation because there are real affordances to how, say, convection currents form in the mantle and then push on the plates. So you want them to understand kind of the spatial layout of the layers of the Earth and the causal and dynamic processes inside the Earth, like subduction and convection, etc. And then how those plate tectonic phenomenon give rise to the things that we see on the Earth, like earthquakes, volcanoes, seafloor spreading, mountain formation, etc. So that's an example of how these various knowledge ontologies are used in a progressive model building way to develop a really rich and deep mental model that is very accessible to the students, and it's presented in a way that doesn't overload them in terms of working memory and such. And these levels of knowledge build really nicely and concretely on each other and capitalize on these visual and perceptual affordances.
So a student who's modeled the structure of the Earth would be able to draw that sort of diagram of the concentric circles because they'd already have that concept.
Right, exactly. And I've done a lot of pencil and paper tasks working with students one-on-one in their drawings. It's very fascinating to see how their drawings can be used as a mental model of what they're thinking and how their inferences are really tied to that mental model. So for example, I had in my 2000 paper in the International Journal of Science Education, I interviewed a series of students, and I had one student who thought that the Earth, the core was sort of in the bottom, so it was like a hard-boiled egg, but the core was in the bottom. So what's interesting about this mental model is that perceptually, you can't use it as a representation to understand convection. So she had that convection currents rise, and that was very consistent with this buggy model, right? Because if you have, conversely, a mental model that has the core at the center and the magma around it, you can begin to understand how convection currents can form within the mantle layer. So it's really interesting how her mental model created kind of a barrier for deep inference making and got in the way of this progressive model building.